Konnichiwa. Watashi wa Nihongo ga hanashimasen. Unfortunately, that's all the Japanese I managed to learn for this talk, so the rest is going to be in English. That said, I translated a few slides into Japanese, so that's the title of my talk in Japanese. The second line there is my name in Japanese. For some reason, they look pretty similar to me. If you understand Japanese, maybe you can explain that to me later. Anyway, I'm Godfrey. You can find me on the internet as Changing Code. You know I'm legit because I have the same shirt as that guy on GitHub. I am a speaker here at RubyKaigi. You already know that. But I thought that was pretty cool when I saw that yesterday because those Chinese characters actually mean something else in Chinese, probably more like this. So if you would like to be an author climber, you should probably come speak next year. Anyway, I came from a land far, far away called the United States. In case you don't believe me, this is a picture of me enjoying some authentic American cuisine at Portland Airport a few days before I came here. Even though I live in the States, I'm actually a Canadian, and this is a picture of me representing my country on a TV show in the United States. So given my unique background, I thought I would do a little bit of cultural exchange thing and introduce you to my country. So this is how we report temperature in Canada. You're probably wondering what that C stands for. Turns out the system is invented in Canada, so it stands for Canada. And if you use it in a sentence, you usually say it's 14 degrees in Canada. It makes a lot of sense. Right. So even though it's invented in Canada, it's actually pretty popular here as some of the countries that uses that system. On the other hand, this is how they do it in the United States. You're probably wondering what that stands for. Obviously, that stands for freedom. So the system is called the degrees of freedom. So you should say it's 57 degrees of freedom. And this is a list of countries that uses that system. Anyway, if you want to know more about Canada, you can run German-Canada on your computer, which allows you to program in Canadian accent. And since this is RubyKaigi, I would like to mention that it's also available for mRuby. So anyway, you're probably wondering, what is this guy doing? Where's Yehuda? Well, it turns out that on the web, there's a thing called default, so you have to scroll past default to see me, but I'm there. The lesson here is always check to find print, so you don't end up in a bait and switch scenario like this. Anyway, let's talk about Ruby. So Ruby has many strengths. So there's a lot of great things about Ruby. It's high level, it's predictable, it's dynamic, it's object-oriented, it supports metaprogramming. Since you're sitting here, you probably don't have to sell these to you. You know why it's great. But Ruby is also pretty slow. It might get 3 times faster in a few years, but unfortunately, the current state of affairs is that it's pretty slow. That didn't turn out to matter for the most part. As you can see, there are a lot of companies building big apps like Rails app on the web, and for the most part, it's fine. But occasionally, there are certain things you want to do that Ruby is just not fast enough for. This is not unique to Ruby as well. You might hear a lot of people do. A lot of people are doing some machine learning or number crunching things in Python, but turns out the most intensive parts are actually performed in C. So on the flip side, there's C, which is low level and it's pretty imperative. It could be pretty dangerous, but on the bright side, it's pretty fast because it's pretty close to metal, right? So in Ruby, you can get the best of both worlds by writing native extensions. So for example, when you run gem install JSON on your computer, it actually ships with two implementation. So first there's JSON pure, which is like a pure Ruby implementation of the JSON encoder. But if you are installing this on a platform that supports it, it would actually use the native version, which is written in C and a lot faster. So as a user, it's completely transparent to you, and you just get the benefit of the speed of C when transparently. You just invoke it like your normal Ruby methods, but it's under the hood, it's actually completely written in C, so it's very fast. So there we have it, native extensions. By now, you've probably learned to read the fine prints. So as you can see, there's a star there. What is the fine print? So this is obviously great for the end users, but as a person writing the native extension, it's not so fun, right? Like you have to write code in C, like we said, it's like dangerous, it's low level, it's not OO, it could be dangerous, and that could also mean that it's not that great for the end users, because if you made a mistake, it might crash the entire process at runtime, it might segfault. So I am a member of the Rails core team, and DHH, the inventor of Rails, taught me a thing. In Rails in general, we try to, when we want to implement certain features, we are willing to jump through some hoops under the hood to make the thing nice to use to the user. And I would take the liberty to extrapolate that a little bit. It's not just to make the API look pretty. It's we are willing to jump through hoops in the implementation side to make the whole experience nicer. And a fast experience is good experience, right? Like no one likes slow code. So, right. So basically, we should, like when we can, we should try to do whatever is in our power to make things fast, so you can just benefit from it without knowing what's going on under the hood. So you might have heard of Sam Saffron. He did a lot of performance work. He also ran a pretty big Rails app called Discourse, and he spent a lot of time on performance, and he spent some time profiling Discourse. And one of the things that he noticed is that there's a method called string.blank that shows up on the profiler output a lot. So this is the implementation in active support. It basically checks if a string consists of only of white space characters. This is pretty simple. This is pretty easy to read. And unfortunately, this is used in a lot of places unexpectedly. And this turns out to be a somewhat costly thing across the entire request, because it's called multiple times, and like this is not the fastest implementation and stuff. So what he did was he wrote a C extension for that that re-implements that same method in C, and that's great. It's up to 20 times faster. And I would hypothesize that in Rails or even in your app, there are probably some opportunities like that where you can basically re-implement a pretty stable part of your program in C and get some performance benefit from it. But I'm not Sam Saffron. I'm not a C programmer. I know just enough C to be dangerous. When I program in C and I see a variable, if it doesn't do what I want, I probably add a star. And if that still doesn't work, probably add more stars. If that still doesn't work, maybe use ampersands. So the crazy thing about this is I can actually write a C program that compiles, but at runtime it might blow up on me unexpectedly, and I might or might not be able to figure out what's wrong. So personally, I would feel pretty nervous about shipping something, like writing a native extension and tell people to use it in production and have to support that. So recently I joined a company called Tilder, and Yehuda is my coworker, and he's also on the Rust core team, so it's telling me, hey, you should probably learn Rust. So I guess I will let Yehuda tell you why you should perhaps care.
Hello. I apologize in advance for how fast I talk. Every time I come to RubyKaigi and speak, the only thing I hear back afterwards is, that seemed great, but it was so fast. Can't really do anything, I'm sorry. So I also was on the Rails core team. I'm now a Rails core alum, and I spent a long time on the Rails core team trying to make things faster. That was the original pitch that I had. And unfortunately, one of the things that was sad about trying to do that is that in Ruby, the cost of abstracting something you may want to abstract something for developer experience to make it easier to plug in or something like that, but that always has a cost in performance. So it's very difficult to achieve both your goals in modularity, which is a big goal I had at the time, and also performance. And it turned out we got modularity and we got not as much performance as we would have liked. So I worked on the Rails core team, and that's that story. I also more recently joined TC39, which is the committee that makes JavaScript. And I've worked a lot on that committee and learned a lot about language design. And it's pretty fun. You should definitely check out JavaScript. I think I'm pretty impressed with what we've done as a committee and how JavaScript has been going. So if your view of JavaScript is still stuck 5 or 10 years ago and you think it's a terrible language, you should probably keep an eye on it because it's getting better. But finally, I also recently joined the Rust core team. I guess I traded the Rails core team for the Rust core team. Up or down, I'm not sure. And the Rust project, our motto is called Hack Without Fear. And that's basically the same story that Godfrey was telling before, which is that there's a lot of people who want to write low-level code. They really would like to make something faster. And you may remember that very early on, DHH talked about Campfire, and he said, we were able to make Campfire fast because we wrote it in C. And people thought that was cool. But in practice, very, very few people writing Ruby programs want to take some time out of their day, switch from Ruby into writing C. And at least for me, I didn't feel confident that I could get away with it, and that I wouldn't end up blowing up my app in production or my users' apps in production. So for us, and for me, the thing that's great about Rust is that it's all about allowing people to hack at the low level, at the bare metal, as Godfrey said, without fear that you're going to end up having the bomb drop in production. So let me talk a little bit about how Rust works, and then we'll get back to how it fits into Godfrey's introduction. So first of all, if you've ever, how many people here have written C code before? Okay, awesome. So the basic unit of data in Rust is called a struct, just like in C. And so you can write a struct and you can write some fields on it. And then unlike in C, if you wanted to write some functions that worked with it, you would write the functions and you would take the first parameter would be the struct that you just wrote. In Rust, you can write that as in an OO style. So you can say, I want to implement some functions for circle, and then you can make some implementations. In this case, you can see that there's both a class method called new and an instance method called diameter. The new method is like the Ruby new method. It lets you construct a new circle, and the diameter method is the method that actually takes a circle and gives you back a number for its diameter. So it's a struct in Rust is OO, just like in Ruby. Now, if you want to use a struct, here's how you use it. The main function in this example is the main function like in C and many other languages. And you can see here that the class method works the way you would expect. The colon is in Ruby, the colon is optional. In Rust, the colon is how you talk about class things always. So circle colon new 10.0 gives you back a circle, and then you can call its diameter method. Also note that you didn't have to type any type annotations here. That's because inside of a function body, the type inference system works very well. So could see that I was making a circle and made that the type. So that's pretty simple. That's basic OO. And the key thing about methods in Rust, and this should be clear so far how it works, is that the compiler basically knows exactly what implementations you're talking about, just like the C compiler does, even though you're using methods, right? So in C, the reason the compiler knows is because you have a function, it's named something in particular, you call it, of course, the compiler knows what function you're talking about. In Rust, even though the system is OO, and we'll get into more detail soon about how that continues to work as it gets more complicated, even though you're using methods, the compiler pretty much always knows exactly what function you're calling and statically dispatches. Now, the thing about static dispatch is that when you first hear about it, when someone says, This allows static dispatch. You think, well, what's the difference in cost between a static dispatch and a dynamic dispatch? And maybe you say, well, like the Go programming language has made dynamic dispatch very fast, like almost as fast as static dispatch, so maybe that doesn't matter that much. But the thing that really matters about static dispatch is that static dispatch allows function inlining. What that means is that if you know exactly what function you're calling, it's not only that you can make calling the function fast, you can actually take the function and put it into the place where you're calling it at compile time. And that isn't the end of the story either, because function inlining is the first optimization that you need to get all the other optimizations that you could possibly do, right? So at compile time, if you don't know where you're going, if you don't know what function you're calling, you obviously can't do anything else. But in Rust, the fact that many things Rust knows what you're calling mean that when you do, for example, a loop with a closure, which Godfrey hasn't had it as an example before, Rust knows that you're calling a function, it takes a closure, it knows what the closure does, it knows how that all fits together, and then it can give to LLVM something that LLVM says, oh, I see, that's just a loop. I'll just make a loop out of it. But you can't even get off the ground if the method, the all method in that example, was just dynamically dispatched. You can't even do anything at that point. So I usually call this a gatekeeper optimization. It's an optimization that unlocks all the other optimizations, and it's a very important part of Rust. Almost every function or method you ever call is always statically dispatched. And the J9 talk earlier and the JRuby talk earlier sort of talked about optimizations that you could do with Ruby, and a lot of them, in fact, require knowing where you're going, or at least figuring it out eventually. Now, in addition to knowing what function you're calling, another thing that makes a big difference in performance is where exactly you put the values that you are working with. And a normal way that you store your values is storing them on what's called the heap. And in Ruby, if you write a Ruby program, all your values are stored on the heap no matter what. And this is how you do it in C. This is very scary to me, not just because of the syntax, which is crazy and easy to mess up, but also because once you allocate something on the heap and start giving out references to it, you're required to free that thing that you just allocated, so it's up to you to free it, but you're not allowed to free it if anybody else points back at it. Right? So now you have the system where you have created an object, you've given it out to people, you're required to free it, but you somehow have to know that they don't have any reference to it. Of course, this is very complicated and hard and is the source of pretty much all the reasons why things crash in production. Now, stack allocation, if you've written this C code, has a little bit of a nicer syntax. And let's look how it works. So this is some C code. On the right, you see the stack. And what happens when you run this program is the first thing that happens is you enter the main function, and the compiler has looked at the main function, and it can see that we have both a square that exists in the world, and we also have the return value of diagonal. Both of those exist in the world, so the compiler can see that we need some space for them, and the compiler has said whenever you enter this stack frame, just in addition to whatever else information you need, leave some space for those things. And so when we go and we, say put 10.0 into the side, the first thing that happens is that slot that we saved off before our compile time now gets filled in with the information. And when we go to invoke that diagonal method, the first thing is we get a new stack frame that has whatever information diagonal needs. But then when it returns, that fills in the information, the slot that was put on the stack for the return value, and we print it. And then here's the important part. Here's the part that really matters. When you're done with the main function and you return, you can simply pop that stack frame, and you don't have to do any kind of freeing. You don't have to do any kind of special syntax. It's just a part of the programming model that all those values go away. So the nice thing about stack allocation is that, first of all, the stack pointer is the thing that handles freeing memory, and you already had to have one of those, right? So you already had to have a stack pointer to run your program, so the stack pointer is also responsible for freeing. That's great. Now, one thing to note is that I sort of said that in Ruby everything's heap allocated. In most garbage collected languages, there are some situations where you get stack allocation, but it's never guaranteed, so you can never rely on the fact that it's happening, and small changes in your program may cause something that previously was stack allocated to become heap allocated. And there are some pretty bad downsides. So first of all, in order to do stack allocation, you have to know the size of the function at compile time, which means that if you get more and more abstract, it's hard to know exactly how much space to leave. But the second part is perhaps the more important one, which is that if you stack allocate something and you make a circle on the stack, every time you give out a pointer to that circle, it's super dangerous, because if that person hangs onto that pointer and tries to use it after your return, then the universe explodes or you segfault. And in fact, this is also a very common reason that things crash in production. So what ends up happening in practice is that people are really want to stack allocate because it's fast, but in practice, people are scared of stack allocation, and there may be a lot more heap allocation in programs in C simply because people are afraid of the consequences. Now, in Matz's keynote, he talked about the possibility of using the ownership model to help eliminate the GIL in Ruby, some future version of Ruby. The nice thing about the ownership model in general, the reason why that makes some sense, some amount of sense, what Matt said, is that Rust ownership makes the idea of stack allocation safe, right? So when you are thinking about, okay, in both the heap case and the stack case, the problem that we're encountering is, okay, so I allocated something, I made a circle, and now I'm giving it out to some people, and as soon as I give it out to them, I can't know when they're going to be done with it. They can hang on to it, they could put it in another struct, they could put it in a closure, they could do whatever they want, and I can't be sure that I am allowed to free it. And the basic idea behind Rust ownership is that through the compiler, you can be sure that if I allocate something and give you access to it, either I am no longer allowed to access it anymore at all, or the other person has to give it back to me and is no longer allowed to access it. So the concept of ownership is basically just a solution to this problem of I have these values, they exist somewhere potentially dangerous with some rules about when you're supposed to free it. Ownership guarantees that that problem does not exist. And so you can hand out pointers to the stack without fearing segfaults. So that's the basic idea. But perhaps one thing that you might have noticed is so far we talked about structs and methods, and while the method syntax is certainly nicer, it's more pleasant than the C function syntax, so far we didn't talk at all about how you could do anything like polymorphism, or you have one method that means different things depending on the type that you're dealing with. And of course, in OO, a language with support for OO would not be worth a lot if you couldn't ever have polymorphism. So I want to talk about how that works in Rust. And importantly, as soon as you get polymorphism, now there's an important problem, which is how do you make sure that you aren't going to end up in exactly the original situation where everything is dynamically dispatched and you can't actually do any of the original optimizations, right? So we talked about how you can do all these optimizations if you know exactly what method you're calling, but as soon as one piece of syntax might mean many different things, you have to understand how do we get away with saying that those things are still known at compile time. So in order to explain that, let me first talk about how inheritance works basically in Rust. So in Rust, if you want to describe some shared behavior, like what we in Ruby would use a superclass for, the way that always works is traits. So there's no kind of traditional class inheritance in Rust, but there is a way of describing shared behavior using traits. Here we have two structs that describe the concept of a shape, and we would like them to have a shared method. In Ruby, we'd probably create a shape superclass and have it both inherit, or maybe in Ruby we'd use a mixin for that. In Rust, what we're going to do is we're going to make a trait called shape, and that shape trait says that it has a method called area and returns an F64, and then we implement that method for each of the two types that we care about. You can implement a trait for any existing types. You can even implement a trait for built-in things like I32, like a 32-bit integer you can implement a method for. So it makes them a little bit like Ruby refinements, right? You can refine existing methods that exist, existing types that exist, no matter who made them, and you can use them as long as you explicitly imported them. So now let's look at how you actually use one of these things. So we have the circle and square and shape traits, and we have implemented them. And you can see in the main function here, we have created a square, we've created a circle, and then we call the area method. And you can see here, it's not so hard to figure out how Rust will ensure that that area method is pointing at the right thing, right? So in the first case, we're talking about a square. So Rust knows, okay, we should use the first implementation. We're talking about a circle. Rust knows you should use the second implementation. And again, we still have static dispatch. Even though we're using method syntax now and we're talking about a trait, a method defined on a trait, we still know exactly what we're talking about. But perhaps even more interesting, you can make a function that takes a type that implements a shape. So you can say, I'll take anything that implements shape, and then you can call area. And the way Rust works here is Rust is saying, I'm going to make a special version of this function for every single person who calls me, every single type that calls me, that is, again, statically dispatched. So this print area function, even though it is completely polymorphic, right, it's completely takes any shape and then calls a method on it, it's still guaranteed to be statically dispatched, which means when you use it inside of a loop, or if it implements a loop, all the original optimizations that we talked about will continue to work. And even though we as humans don't actually know what that area method is doing, the compiler knows, and that's the important thing here. And really the whole story here, the story of all the things I just talked about are that the difference between heap allocation and stack allocation matters, just a little bit per time, and the difference between stack pointer bumping and freeing matters a little bit each time, and the difference between static dispatch and non-static dispatch, inlining and not inlining adds up, makes a little bit of difference a little at a time. But when the programming language itself makes as the main idiom stack allocation and static dispatch, the combination of how that all works in practice ends up adding up quite a bit. It ends up being very powerful. So all the dance that Rust makes you do to explain what's going on simultaneously makes things safe, like we get from a language like Ruby, and fast, like we get from a language with C, by describing your intent to the compiler in a way that mostly matches what you would have had to say anyway. The compiler can both check you for making safety mistakes and make smarter optimizations. So the difference between heap allocating everything, So going back to fastBlank, right? So going back to fastBlank, which is the method that we talked about in the beginning, let's again look at the C version of that. So the C version has a bunch of annoying stuff at the top and then a big switch statement. And the reason the C function is written like this is because if you start abstracting things too much, you're going to get yourself into trouble. So you basically just inline the universe. This is sort of how people write C. And then again, let's look at the implementation in Rust, right? So the Rust implementation is that we have a function. It declares itself as being compatible with C functions, and then it just does a few methods. So there's a method, another method, there's an iterator involved, then we have a closure, another method. So you might expect, looking at this, if you didn't hear me give the spiel about how Rust makes this fast, that this would end up being much slower than the C equivalent. But in practice, all the things that I just talked about, even though it looks like something you might write in Ruby, ends up meaning something quite different in the Rust programming language. So let's look at how it benchmarks. And the first time I saw this, that was my face, basically. Not yellow, but I was still, that was my face. And first time we ran it, what we noticed is that the Rust code is actually faster than the C code. And I guess in this particular example, it's a tiny, tiny bit slower. But I know I'm actually reading this completely wrong. Yes, the Rust code is faster than the C code. It's 11 million instructions per second instead of 10 million instructions per iterations per second, and the Ruby code is only like 1 million, right? So it's like 10 times slower. And I was very surprised the first time I saw this, and actually seeing this the first time when me and Godfrey were was teaching him Rust for the first time, seeing this made me actually go down the path of trying to understand exactly how this ends up being faster, and that's what this talk is really about, right? It's about saying there's all these things that don't look like you're saying anything special, but by making the idioms a little bit different, making each idiom a little bit different, stack allocation as the main thing, closures as the main thing, all that stuff ends up meaning that things become fast.
So this is a function Yehuda showed you, and this is basically the entire fastBlank implementation in in Rust compared to like the many lines version in C. But there is a fine print. What is the fine print? Well, what Yehuda didn't show you is the glue code. So this is the entire extension after adding all the glue code to expose the method to Ruby and stuff. So the yellow part is the function that we just showed. That's like the one-liner implementation. Unfortunately, you have to write all of these glue codes, some in C, some in Rust, because like there are some like certain things in Ruby are exposed as like macros instead of functions, so you can actually call them in Rust, right? So so you have to write some C glue code and some more glue code on the Rust side, primarily to transport like types between Ruby and Rust. So if you put them side by side, you see that you like actually it kind of like it kind of defeats the purpose. Yes, the implementation on the C side is much longer, but you have to write all the glue code to glue it together, and they end up being roughly the same number of lines of code. Fortunately, the glue code is very generic, so, and in Rust, as Yehuda pointed out, you can do a lot of abstraction for basically for free. So what I started working on is to create a library in Rust called libc Ruby, and with that, I was basically able to take away all the glue code and put it into a library that you can just use, and basically this is the entire Rust extension using the library, and it's so tiny that you can actually fit the whole thing on the screen, and basically you use the library and you import some types and you implement the function as before. And you can even define the init function in Rust, and that's basically it. What's interesting here is that you can, if you've written C extensions or written C code, basically because of the dynamic nature, you have to use value pointers everywhere. But in this case, you can actually tell the compiler that you're expecting to return a Ruby Boolean here, and if you return wrong type, or if you forgot to return something in one of your if branches, it would actually not compile. Another example is that this is how you would attach the method to Ruby. This is actually talking about the string type in my library, and if you look at the implementation, it's actually basically talking about the RBC string pointer. But we were able to annotate that with a lot of type information, so the compiler actually knows exactly what is going on, and as you can see, eventually it basically just called RB-define method ID in C. So you can write something like this that eventually just compiles to literally that line, but with a lot of safety checks, and also it's a lot more expressive. Likewise, you can write something like this, which basically compiles into the imperative C code that is simultaneously easier to read and also safer. Finally,
I guess we'll just both stay on stage at this point. So what Godfrey just talked about is sort of attacking the problem of writing Rust code that understands Ruby from the Rust angle, right? So from the Rust perspective, you really would like to be able to write code that works with Ruby objects in a way that is pleasant for Rust. And importantly in Rust, it's very important, just like when you write Ruby, you don't expect to use a random Rust library and have it segfault. You're required to actually call those things unsafe in Rust, and we don't want to call our library unsafe. So we have to figure out how to make working with the Ruby C API perfectly safe from Rust, which is a tall order. It's quite hard. And so that's what Godfrey was talking about. But from the perspective of Ruby, there's also another thing, which is that even writing the code that defines methods and classes and constants and all that stuff is pretty annoying to write, even if you have nice abstractions, right? And what you really would like to be able to do is you'd really like to be able to define classes, methods, instance variables, all the stuff that the Ruby C API lets you define about a class. You would like to be able to use class syntax to do that. And so the idea behind TRB files, which is the other half of the project, of the Turbo Ruby project, stands for Turbo Ruby, is that you write everything about the Ruby structure of what you're building, the classes, modules, constants, just using regular Ruby syntax. And then when you get to a point where you want to start talking about Rust, then you embed some Rust code that can call into a library that looks like what Godfrey showed before. So that way you have completely eliminated the glue code from both directions, right? All the code that makes coercing values from C back into Ruby values, that stuff goes away from libc Ruby, and all the stuff about how you define the structure of your Ruby objects, that goes away from Turbo Ruby files. So how does that work? So the way it works is that you include the Turbo Ruby library in your xconf, you would run it, that would emit the appropriate files, and then you could just use it like any other shared library. So the basic idea is that we would like this slide over here. So in practice, you of course end up needing a lot more Rust code, but we would like this slide to be the only thing you have to write to get the hello world going, if you're willing to embed the Rust code. In practice, of course, you end up with a bit more Rust code than this. This would not make sense to be the entire thing you did. But the fact that this works eliminates any excuse that you have for not trying to use Rust for something small. So basically the idea is that the TRB file, which is effectively describing the structure, and libc Ruby, which lets you safely work with Ruby objects from Rust, if you combine those two things together, you get something that lets you very pleasantly, and even on the weekend, or I normally hack after like 10 p.m. at night, after my day job. Even when you're pretty tired, you can still get the job done. And I think for me, the fact that I'm mostly hacking at 10 p.m. at night means that I have basically 0% chance of ever writing anything in C, because I'm pretty sure that I'm going to mess it up at that point in my life.
Okay. So I realized we didn't actually include the GitHub link in the deck, but it's in tilde.io/turboruby. Be warned, it's major work in progress, and like it's my first Rust project. So, you know, you can check it out and see how we progress, but don't don't use it in production yet. Maybe one day it will be good. Finally, right. So the title of the talk has Rails in it. So basically the entire exercise is me wanting to write some part of Rails in C extension. So this is basically still a work in progress, but I started. I think I have bootstrapped enough of it that I can now do things like blank in Rust, and I can do things like active support duration in Rust, which is not in itself, it's not a major performance bottleneck, but it's like a good enough exercise to prove the concept. So in the future, there are probably more parts like the JSON encoder, or like maybe the action dispatch, like the router code that is like fairly self-contained and fairly stable at this point, that could benefit from a little bit more performance. And finally.
Yeah, so finally, yes, like I said earlier, Matt's mentioned trying to remove the GIL, and also the idea that we might be able to learn from the Rust ownership model for doing that. And I want to talk a little bit about both how things that we have encountered in the Ruby C API that make working with the ownership model in Rust a little trickier or too coarse-grained, that maybe if we started working towards making Rust interop better, that would open the door for more general ownership-based optimizations or ownership-based work in the future. So first of all, I want to say what basically the Rust story is for ownership in like a nutshell, which is that you get shared state or mutable state, but only one of them at a time, right? So if you think about how most of the time, so everybody knows shared mutable state is the root of all evil, right? And so most of the time what people do when they're trying to find a solution is they'll either go with like the channels model, the actors model, which basically says you have a value and you can only use it in one place at a time, and what that means is don't allow sharing or aliasing, right? You can only have one at a time. One thing can see it at a time. And then there's the sort of the functional story, which says you can't mutate anything ever. So because you can't mutate anything ever, we can share as much as we want, but we don't have to worry about people changing something and causing the kinds of problems that causes. And it's important to realize that both of these things are whole programming model things. They're saying you should always use immutable data structures everywhere in your program because of the fact that we want to forbid mutation, or you always have to use channels everywhere in your program or actors everywhere in your program to forbid aliasing. And the Rust story is actually something in between. It says per thing that you're doing, per moment, you can either have sharing or you can have mutability, but not both at the same time. So Rust safety guarantees basically boil down to you can either have as many read-only aliases as you want, or you can have exclusive ownership, but you can't do both at the same time. And interestingly, the Ruby internals, so Rust actually does this statically. So Rust normally does this using static checks, but Rust also has a thing called refcell, which is basically a dynamic version of the same thing. It lets you use dynamic checks to make sure that you're doing the right thing. And interestingly, Ruby's freezing model, Ruby freeze, is pretty similar to what you might want in order to say that you're not allowed to mutate something temporarily. But there's nothing in Ruby that lets you take out exclusive access to something. So there's nothing that lets you say, I want to have exclusive access to this object, and I want to be allowed to mutate it, but no one else can see it at the same time. The exact way that can work is tricky. The JavaScript programming language has a similar problem for web threads, and it uses a strategy called neutering, which is basically to take whatever data was inside of an object, move it into a new object, and then set a flag on the original object that says if anybody tries to access this, they cannot access it anymore. Great, I will wrap up. So there are strategies for dynamically doing the thing that needs to be done here, and it would be really great in the Ruby, if the Ruby VM had support for expressing in a first-class way both temporarily freezing and temporarily gaining exclusive access in a way that was guaranteed to work in the VM, because then the Rust libraries that we're writing could take advantage of them, and we also hypothesize that that will have advantage when we try to remove the GIL and do other things in the future.
So that's basically it. I think we don't have time for questions, so maybe we can grab lunch together or something. Yeah, that's it. Thank you very much. ありがとうございます。